Hello, I welcome you all. The problem reads draw the shear and moment diagrams for the beam. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.S. Hibbeler. Okay, we have a cantilever beam. Okay, let me just redraw it here. I think somewhere here, like so. Right. Okay, let me call this point here. Okay, let me draw all the lines that I'll need to use for both my shear and moment. Right, so let me call this point as my A, which is fixed. So I expect the reactions here. Okay, we move this down. I'll use them later on. I move them somewhere there. Alright, I think I just moved them. I'll use them. I'll withdraw them later on. Okay, I have AX there, and then I have my moment, which is MA. Then later on I have my load, like so, these triangular loads like so. Okay, and then of course this is AY, and then the dimensions are given is 0.5L, 0.5L. Alright, so this is the loading like so. This is the loading like so. W, right. So we expect our equivalent forces to be, let's say, somewhere there. This is going to be equal to half. This is 0.5, which is half, times 0.5 L times W. Okay, therefore this is equal to, if we do the multiplication, this gives us, so our equivalent force is equal to half times W times 0.5 L. This therefore gives us 0.25 WL. So we have 0.25 WL, and also here is the same 0.25 WL, and this position that this point here is 0.25. This position is 0.25. No, sorry, is 0.5 L divided by 3. Okay, so this therefore gives us a value of 0.117. Okay, all right, let me write it there. This is 0.17 L, and also this one here, it is 0.17 L. Okay, that's 1/3 of 0.5 L, right? I mean, maybe yes, 1/3 of 0.5 L. Okay. Right. 1/3 of 0.5 L. So let's go ahead and now find out everything, the supports. So summation of moments about point A equal to 0 and clockwise being our reference. What do we have? We have 0.25 WL, right, times, and this is a negative moment, times 0.175. I think maybe for the sake of rounding off, let me just write so that I write it just as this is half L by 1 over 3, which is just 1 over 6, right? So let me just indicate it as 1 over 6. So it's L over 6, and also here is L over 6, right? So that I don't lose out my number so much, 0.6, like so. Alright, and then we have the other one also minus 0.5 WL. This one is 0.5 L plus L over 6. Alright, and then finally we have plus MA equal to 0. Therefore, MA is just going to be equal to, let's do the math there. So we have minus 0.25, okay, minus, let me sum them up, minus 0.25 over 6 WL squared minus 0.25 L squared by 0.5 WL squared. Then we have plus minus 0.25 divided by 6 WL squared. Alright, this gives us, what do we have? So we have minus 0.25 divided by 6 minus 0.25 times 0.5 and minus 0.25 excuse me, divided by 6. So this gives us a 0.2083 WL squared, right? Is that correct? 0.25 divided by 6 minus 0.25 by 0.5 and minus 0.25 divided by 6. Okay, this is fine. Then we have summation of forces in the y direction equal to 0, like so. We have AY minus 2.5 WL minus 0.25 WL, then plus L, okay, AY I've already indicated it, therefore this is just equal to 0. So AY is going to be equal to 0.5 WL, right? 0.5. And then summation of forces in the x direction equal to 0. In this direction we expect AX to be equal to 0. So let's replace these values. So we have AY equal to 0.5 WL. Then we have MA equal to 0.208 WL squared, right? Okay, it's a little bit long. This 0.2083 WL squared. Okay, and then this one is just equal to 0. Great, I think we are done. Okay, let me wrap this so that we start drawing. Okay, let's draw our lines where we're going to draw our shear and bending moment diagram. Okay, from here to there, and then from here to there. All right, great. So this is our shear force diagram. This is our bending moment diagram, and we have something like this: plus minus 0, plus minus 0. Great. Okay, so I start drawing. Again, we are not going to do the shearing, which we could have done, but instead we're just going to use the differential equation that relates the loading, distributed loading, to the shear as well as the moment. All right. So we have at A, at the fixed point there, A, we have the shear, positive shear that goes up. So we have this shear that goes up with a value of 0.5. Okay, let's just come up to there, something like this. Okay, so if this is 0.5, all right, so this one is 0.5 WL. All right, and then from A, let me call this point B, then this one C. From A to B, I'm calling this point as A, then B, then C. So between A to B, we have the distributed loading, and we know that if the loading in this case is of course negative and is decreasing, all right, it's negative and decreasing, therefore we expect the slope for the shear to also be negative and decreasing. All right, so if that is the case, uh, we expect the slope to decrease. So let's find the value. So we expect it to be something like this, right? To decrease. So we don't know what it is. Let's increase this value. We increase it a little. Okay, let's find the next point at B. We're going to move it later on. So we have 0.5 WL. Then it will be um, minus the equivalent force there, which is 0.25 WL. So this gives us a positive 25 WL. So maybe I increase this a little bit. It's a bit short. Maybe I take it somewhere. Let me say somewhere there. I think we still need to increase it a little bit. Let me drop this down a bit, just down, maybe up to somewhere there or somewhere here. Great, something like this. And then let me demarcate this line here. Okay, this one here is quite vital. And then increase this line maybe to somewhere. Increase this line. I need green. Alright, maybe to somewhere there. Great. So let's call this point as our 0.5 WL. Okay, so then we are saying the next point is going to be 2.5. So let's put our 2.5 somewhere here. Let's put it here. Okay, let's put it here. Next point is going to be maybe there. Okay, because we are running out of space. So let's say our point is here, like so. So, and then we are saying the slope is negative and decreasing. So this is the manner. I'm going to have this manner like this. Okay, this is where the slope is negative and decreasing. All right, and then from B to C, we again have the distributed loading, and it has the same behavior. It's negative and decreasing. So let's find the next point. So it's 0.25 WL minus 0.25 WL equal to 0. So it will fall down up to this point. Okay, it's fall down. I think maybe I change this point. I change it, I bring it somewhere there, I make it a little bit shorter, maybe somewhere there like so. Alright, so like this. Okay, so this is our 0.25 WL. Then our next one is 0. So it's also like this. It's a slope that is negative and decreases, and this is 0. Right. So this is our graph. This is our graph. So for the bending moment diagram, let's go ahead to work it out. Okay, let's now draw the bending moment diagram. We are done with the shear force diagram, and like we did for the shear force diagram, we didn't do any sectioning. Rather, we were using the differential equation that relates the loading, the distributed loading to the shear and to the moment. We know that dv dx is equal to negative w. In this case, our load is negative, our distributed load, and dm dx is equal to the shear force. So these are the relations that we are going to use in drawing these diagrams. So at A, we have already an applied moment. We already have an applied moment, but I would want to rewrite this moment, without in its fullness, because since I'm going to use this in my calculation, because I'll be moving from A towards C. But you can also use another method where you would move from C coming the other side. Really, there are a lot of methods. So I'm just demonstrating one method of moving from A to B, since this is how I was working out these problems. I'm going to use MA in trying to subtract the moment I'm going to get due to the loading from A to B, so that I find the moment in B as I begin to draw. So let me write MA. We know that our MA is equal to 0.25 WL, okay, times L over 6, okay, plus 0.25 WL times point times L over 2 plus L over 6. Alright, if we worked out this, we'll find that our MA can also be written as this can be written as 1.25 divided by 6 W L squared, which is also equal to 0.20833333. We keep on repeating itself, right? So that is how I want it, since I'm going to use it in my calculation. So let me write it somewhere. So my MA, I'm saying, is equal to, my MA is equal to, I want to maintain my accuracy. That's the reason I'm writing it like this. 1.25 divided by 6 WL squared. Alright. So let me wrap this. So let's start the work. So at A, we have the moment, the support moment of magnitude 0.2083 WL squared, or 1.25 divided by 6 WL squared. But we cannot write it directly in our diagram here, because this is our support moment. Therefore, when we are using this particular method, let's come to A here. So this is behaving as if it's an applied load at A, okay? So if this is the case, we have this moment like this, which is MA. So what we are going to do is, imagine you do a section of this beam to the right of a very small infinitesimal part, very, very small. If you did a section there and then checked the internal forces, they would find that you are going to find a moment in this direction, right, of magnitude the same as MA, all right? Same as MA, which is just 0.2083 33, okay, WL squared, all right, same magnitude. And this is the one that we are supposed to use when you're using this method. Every time you come across an applied couple moment, okay, you need to section on the side of interest, and then use that as your moment that you are going to use in your diagram. Okay, so I'm going to draw this down like so. It's a negative, so clockwise, that internal moment at that point. There we go. So let's say that is the one there. So this is the one here. So I'm going to indicate it as 1.25 divided by 6 WL squared. Okay, this is our moment here. So with this in mind, from A to B, we have a triangular distributed load, which is negative, and it's negative, this loading, and it's decreasing. And we saw that from this we're able to find the slope of our shear as negative. The slope of our shear was negative and it was decreasing. This we did already in our shear force diagram. But our shear, okay, our shear itself, okay, is positive and it is decreasing, right? And the slope, therefore, of the moment that we need now is going to be positive and also decreasing. And this is what we want right now. We want this, okay? This is what we want. All right. So we know that the slope is going to be something like this, positive but decreasing, right? But before we do so, we will need the moment at B. Like I said, we can calculate this moment directly by just doing a shear on this side and find the moment moving in this direction. This is one of the method which is also simpler. You can do a section like so, or you can do a section this side and move in this direction and then subtract the moment you find from this negative moment, because this 1.25 divided by 6 is negative, and we expect the moment to slowly becoming positive, right? It will keep on increasing from 1.25. We expect it to be more positive or going up. All right, so you can either use this section or the other section. For me, I'm going to do a section here, okay, moving from this direction going like so. This is what I'm going to do. But like I said, you can also do a section there. Okay, use this section to move from there to there. All right. Okay. Of course, doing a section there is much easier. All right, this is much easier. I think so. Okay, but let me do the other one. Okay, because I know you can do also. I just want to do this one. Okay, so if I did a section there, then what I will have is something like so. A trapezoid, right? Trapezoid loading. And this point is my A, and I have my vertical reaction there, which is 0.5 WL. This segment is my X. We are moving from this direction like so. I have my moment here, which is MA. We already know the value. And then I have my shear here, and then I have my reaction, my internal moment M. Then I have my equivalent force, okay, which I want to calculate right now. Then this point here is W. Then I need this point now, okay. So I'll need to find the equation that governs this loading from A going down. So if I was to write it as qx, okay, qx therefore is going to be equal to, the gradient we know is negative, so it will be minus, change in y is w divided by change in x, which is L over 2, and writing L over 2, it becomes equal to, if we wrote this, it becomes equal to minus 2W over L. Alright, I just brought a 2 on top. Then we do have an intercept or a value that is always there, okay, at t when x is equal to 0. So I'll say plus W. You know, I'm just using this equation, y is equal to mx plus c. This is how I found this equation, okay? You can go through this, okay? W is the intercept, alright. And so with this information, so it means this part here is of course this one is not finished, sorry. This is minus WL over minus W. This is just the gradient and then times x, okay, because we have mx plus c. M alone, m is minus W minus 2W over L, that's it. Then X, then plus W. So this is our Q of X, alright. This is minus W over L, X plus W, like that. Okay, so that is our Q of X. Okay, when X is equal to 0, we have W. And then when X is equal to 0.5 L, okay, 0.5 L or L over 2, you expect a 0 at B for the loading, okay? It's the one that governs this. It governs the same equation that will govern even this other portion because they're the same. All right. Okay, so with this information, then we can find the area for the trapezoid. We know area is going to be equal to W plus, remember trapezoid, plus minus W 2W minus 2W over LX plus W, okay, and then times half, then times the height, which is X. All right, and then when we write this and this 2W by half, then this just becomes W. So this and the half there, this just becomes minus Wx squared divided by L, and then the two add, then times half, then the two cancels out, so this just becomes Wx. So this area is the equivalent force, that's the equivalent force, okay? So Wx squared divided by L plus Wx, okay? There's no need for us to find the equivalent, I mean the location, because we are not calculating moment, we just want the equation for shear, which we are later on going to integrate so that we find the moment at B. This is one of the method, not the only method, okay? Great. So with this equivalent force here, with this equivalent force, we need to apply, with this equivalent force that we found here, we will need to apply the equations of equilibrium, okay, in the y direction. So summation of forces in the y equal to 0. We have minus V plus 0.5 WL and then minus WX squared over L, WX squared over L plus WX. Okay, equal to 0, right? In fact, this one is minus like so, all right? All right. Therefore, our V of X is going to be equal to WX squared over L, all right? Then minus WX, then plus 0.5 WL. Okay, so that is finally our equation. This is find our equation, okay, and you can check it out. You can check this equation for the shear diagram in the interval a to b. Okay, so with this equation we are now going to do the integral. So moment at b is going to be equal to 1.25 divided by 6 wl squared. This is a minus moment, plus integral from 0 to 0.5 L and wx squared divided by L minus wx plus 0.5 wl dx. Therefore, our MB is going to be equal to minus 1.25 wl squared divided by 6 plus wx to the power 3 over 3L minus wx squared divided by 2, then plus 0.5 wlx. Alright, and then we need to feed in those constants. If we did so, our MB is finally going to be equal to, let's do the calculation, 0.5 cubed divided by 3 minus 0.5 squared divided by 2 plus 0.5 by 0.5, okay, and then minus 1.25 divided by 6. Therefore, our answer becomes equal to minus 0.04167. We've rounded off this. It goes 66666. Okay. Okay, so let's say we have a value somewhere there at B. Okay, somewhere there like so. Let's say this is our value. So this is our value, which is 0.04167. Since we do not need any more rounding off, we can also rewrite this one. The reason I just wanted to change it into a fraction was to just maintain the accuracy. Is 0.2083 WL squared. Alright, so we have this value, and we know that our slope is supposed to be positive, right? And decreasing. So this is the behavior there up to, okay, we have this behavior like so, decreasing up to there, and it's the same behavior also we're going to have decreasing up to there, where our moment is just going to be equal to 0. Alright, if we did the section this side and moved the other side, we could also find the same value. Okay, so let me just prove that. Let me wrap this. So this is one of the methods. If let's say I did the sectioning the other side, if I did the sectioning the other side, then I'll have, I want to show what it would become. If I did the sectioning the other side also, we are moving in this direction like this. So I have my shear like so, I have my moment like so, and then my equivalent force here, my equivalent force is going to be equal to, this is half, okay, times, this is x, this is x. The function that governs this, the slope for this function, this function, like we said, all right, is going to be equal to, if we are moving from this direction, you expect this is w divided by L over 2, which is 2L like so, okay, and then times x, right, and then we multiply it. If we wanted to find the equivalent force is going to be equal to half times, of course, 2Lx over L, and then times x. Therefore, this becomes equal to Wx squared over L, which is this value here. Okay, so this becomes a Wx squared over L, like that. Is that fine? Great. So with that value there, again, we are not interested to find, I just want to still just integrate it. We know already is centroid and so on. You can find the moment directly, but I'll still integrate it. So if we had to sum up the equations of equilibrium in the y direction, you have V minus Wx squared over L equal to 0. Therefore, V is equal to Wx squared over L. So if we integrated this moment at B, this would be equal to, from 0 to 0.5, okay, Wx squared divided by L dx. This gives us a Wx cubed divided by 3L from 0 to 0.5. And this gives us 0.5 cubed divided by 3. Gives us a 0.04167. Okay, gives us that value. All right, so it gives us the same value. Okay, of course here there is WL squared. All right, so it gives us the same value. If you wanted to just without doing the integration, you say summation of moments, of course you find the centroid, which is 1/3 of x there. You can still find the same answer. All right, so this is what I wanted to show. So we'll have the same answer either you are coming from this side, going this side, or using the other method. So this moment here is negative. So I hope the video was helpful, and if it was, give me a thumbs up, like my video, and continue sharing my videos. Bye bye, and see you in my next screencast.